Case Western Reserve University's Institute for the Science of Origins proudly presents the Origins Science Scholars Program. The Institute advances the scientific understanding and application of origins and evolution of human and natural systems. The Origins Science Scholars Lectures are presented with the assistance of Case Western Reserve University's Siegel Lifelong Learning Program, College of Arts and Sciences, and Media Vision. Tonight it is my pleasure to introduce Cyrus Taylor, the Dean of the College of Arts and Sciences and the Albert A. Michelson Professor in Physics at Case Western Reserve University. He joined the Case Western Reserve University faculty in 1988 and was chair of the Department of Physics from 2005 until he was appointed dean in 2006. He started his career as a string theorist, but went on to lead an experiment at Fermilab and then a proposal at CERN, and he finally saw the light. And tonight, he'll tell us all about detectors like those that he built. Dr. Taylor.
Thank you very much, Glenn. It's a pleasure to be here. When Glenn and Patricia first asked me if I would be able to participate in the series this year, they specifically asked me to talk about, on the topic of particle detectors as sort of modern cathedrals. And in particular, to talk about what goes into the design and operation of modern detectors. In terms of the scale and magnitude of the projects involved in modern particle physics detectors, it's maybe not quite as long as the centuries it often took to build medieval cathedrals, but it is many decades and involves many thousands and thousands of people. And I hope by the end of the talk I'll give you some appreciation for what goes into all of this. Certainly from a visual point of view, the two images there I think are both quite striking. The particle detector is a view along the beamline of the Atlas detector. And of course, the image to the right is a famous window from Chartres. The one on the left is about 25 meters tall. The one on the right is about 12 meters tall. So, scales are not dissimilar. In any case, in order to talk you through what's really involved in designing and building a modern detector, there's sort of three parts to it I want to go through. First, I'm going to recapitulate some of what Glenn did last week and indeed recycle some of his slides with a review of the standard model, because we don't just go out to build the detectors to build the detectors. We're building it with very specific purposes in mind. And for all of my career as a physicist, it's basically been to try and understand the workings of the standard model, and indeed it's been both an astonishment and a bit of dismay that it works so darned well. Then in particular, what I'm going to turn to is to talk about some of the considerations that go into designing a detector designed to detect the Higgs boson. And then third, I'll talk a little bit about finding the Higgs, and then finally talk a little bit about the work I've done with another detector at the Large Hadron Collider called Totem, which actually is integrated in terms of operations now with the detector I'll spend most of the time talking about during the course of the talk. So with that, part one, review of the standard model, including why is the Higgs boson so important. Glenn liked to use the coffee mug. This actually is my coffee mug. And I decided to use a new photo. It's in a little better focus than the one that Glenn had last week. In any case, so the starting point is that this is, of course, a bit deceptive, right? This is hidden in these symbols are a lot of hidden summations. And in particular, sort of invisible to the eye there, is summing over the different parts of matter that we know about. And there's really 4 different categories that are important in the standard model. First of all are the forces. As Glenn told you last week, they fall into the category of the strong force mediated by the gluons, and then the electroweak force which manifests itself in our world as in terms of photons governing the electromagnetic interactions, and then particles that were discovered, 30 years ago now, the Z and W bosons that are sort of very massive analogs of it. Matter comes in two general categories. First are the leptons, the light ones, which the ones that we're most familiar with are the electrons, since they surround every atom that we're made up of. But they also have sort of heavier cousins, and particularly important for us today will be the muon, which is sort of just like an electron, except a lot heavier, and that heaviness has important consequences in terms of how you design and think about particle detectors. The tau lepton is in principle much the same, but it decays so fast as to be more or less irrelevant for the kind of stuff that we're going to talk about today. And then paralleling that are the quarks, which from a sort of a formal mathematical sense are similar in structure to the leptons, but the difference is that they interact strongly with matter. This has really important consequences as well, right? It results in nuclei that are at the center of all of our atoms. And then finally, at the center of the whole thing, holding it all together, has been the mysterious Higgs particle, which, when I was a graduate student, seemed to be sort of the mathematical device that you used to sweep all the stuff that didn't quite make sense under the carpet, and which we now have discovered and validated its properties. So again, briefly reviewing what Gwen went through. The first term, the F mu nu term, essentially governs the propagation of the gauge bosons, the photon, the gluons, and the W and the Z, and also dictates their self-interactions. And again, the diagrams here are actually shorthand for complicated mathematical expressions, but are really useful qualitatively in terms of thinking about how particles interact. Literally, one can imagine interactions following these kinds of topologies. The second term sort of provides the dynamics for the leptons and the quarks, but it also dictates how they interact with the gauge bosons, with the photon, the gluon, the W and the Z bosons. And this is really important. So that if you look at a diagram like this here, this corresponds, for example, to something like a gamma ray undergoing pair conversion into an electron-positron pair, or a muon-anti-muon pair, or a quark-anti-quark pair, or same thing with, for example, the Z0 or others. Then we turn to the terms involving the Higgs. And the first of these certainly dictates sort of the kinematics of the Higgs, but it also talks about tells us about the interaction between the Higgs and the gauge bosons as well. And so these sort of tightly dotted lines represent the Higgs, and then the squiggly lines are, for example, photons or whatever. And then finally is sort of one of the most mysterious parts of the Standard Model, the couplings between the Higgs and the fermions. And these are important. It tells you how the Higgs interacts with matter. But because of the dynamics of the Higgs, this is also sort of the origin of the mass. This was the part that had been so difficult to figure out before, and is what's miraculous about the entire Standard Model. And then finally, the piece that really makes the whole thing work is the potential. I think Glenn told you last week that dictates the Higgs-Higgs interactions. So you can have Higgs falling apart into two Higgses, or Higgs-Higgs scattering of that sort. But there's really more to it, and I don't think you talked about last week. So we're briefly going to talk about sort of the symmetry of it. So you can think about the magnitude of the Higgs as living along. It's a vector pointing from the origin in some direction of varying lengths. And the potential for it, as a function of that, has a symmetry when viewed from above But it's got the property that the point where the Higgs field vanishes, where you have no Higgs, is not the point of lowest energy. Instead, there's sort of an infinite number of points around a circle in sort of this schematic of it that are all of lower energy, and in fact the same energy, but all of them involve a non-vanishing Higgs field. And it's called, and I've truncated it here, but this goes on off to infinity. And it's called the Mexican hat diagram because it sort of looks like a sombrero. And so in sort of what I'm trying to illustrate here, the gravitational potential of this grapefruit on top of my sombrero here is an analog of the potential of the Higgs field as a function of where it is. So if you really manage to balance the grapefruit on top of the hat and look at it from above, there's a symmetry, right? You can rotate it, and it looks the same under rotations. But that's not actually where the grapefruit wants to live. It wants to live down at the bottom. And anywhere down at the bottom is an equivalent state. But this breaks the symmetry. There's no longer rotational invariance. If you rotate this now, the grapefruit moves. So this is known as a spontaneously broken symmetry. And so if you think about the dynamics of it, if you try and set up the universe in the beginning with the Higgs near the top, any small fluctuation eventually is going to result in an instability, and it's going to fall down and eventually end up at the bottom. And when this happens, when that field that showed up in all those equations actually has a vacuum expectation value, is non-zero in the state of lowest energy, then it contrives to give mass to all the various particles that we have mass, and it does it in a way that is mathematically self-consistent and consistent with the principles of both quantum mechanics and relativity, and that's a little shy of a miracle. Indeed, when Steven Weinberg wrote down originally the model for this 50 years ago this year, he thought it was sort of an amusing observation. But no one thought that the theory was actually self-consistent, and no one referenced the paper for, I think, the first 3 years after it was published. And yet, we now know that this is the most accurate theory ever devised by mankind. So there's a lot of lessons about human endeavor as well as the subtleties of nature involved in that. So the upshot of all this is that the vacuum is really filled with a Higgs condensate that arises from spontaneous symmetry breaking. This, in turn, is what distinguishes the various particles and gives rise to mass. And this is why the Higgs is different from all other particles and why it's of fundamental interest to us. So I've, in fact, gone through a little faster than I had planned to. Questions at this point?
This is out of total ignorance. What is a Higgs concentrate?
Condensate.
Well, what's a Higgs concentrate?
Yeah, so the idea is that every point in space-time, there's this mathematical value corresponding to sort of the magnitude of this Higgs field, how big it is. You would think that in the vacuum it would want to be zero, but in fact it isn't. And so the Higgs condensate is a statement that at every point in space-time, there's this value which is non-zero. And it's aligned at all points in the same direction, and it is the fact that it's non-zero is responsible for what drives the creation of mass in a way that's consistent with relativity and quantum mechanics.
Could you tell me what the L is on the left side of that equation?
Oh, yeah. So this is, we'll go back to the equation. Yeah, so this is the Lagrangian. And so, so Newton, of course, taught us that the particles move according to equations of motion, sort of second-order differential equations, F equals ma. And then you can add in, details in terms of external forces and so on. It turns out that sort of miraculously, that you can derive the equations of motion by assuming that there's a quantity called the action, which is sort of the integral over time of a scalar function, of a function like this. and basically ask that a particle in moving from one point to another, or the universe from moving from one configuration to another, travels in such a way as to minimize the value of the action integrated along the path. And this sort of arose in the late 18th century with some French philosophers, physicists, mathematicians, that sort of approach it by asking the question almost from a theological point of view. If God were lazy, is there some principle that could sort of encompass this by sort of minimal effort, if you like, or minimal action? And so the Lagrangian is the name for it. It's the name for the French mathematician Lagrange. And there's sort of a whole technology called the calculus of variations, by which you look at small changes of each of the variables in there and ask that the result be independent of it. And that then tells you, basically gives you back Newton's equations. And then when you integrate over these paths, over all possible configurations weighted with a phase, you actually reproduce all of quantum mechanics. And this was one of Feynman's great. So it's sort of a central function in physics. If you can write down the Lagrangian for it and combine it with this sort of principle of least action, everything else comes out.
And this spontaneous breakdown in the equilibrium, does that create some energy? And could you eventually harvest that energy out in space, intergalactic space, to drive a vehicle or something like that?
It is interesting that related to this, in sort of empty, in a vacuum, if, for example, you have two conducting plates very close together, there actually turns out to be a force between them as a result of quantum fluctuations that depend on the boundaries there. So people have tried to think about, is there the possibility of something like that? Certainly, as we understand the laws of physics at the moment, it doesn't work. On the other hand, there are from time to time speculations, well, what if we don't actually live in the absolute minimum? Suppose the universe we're in at the moment is actually metastable. Might we tunnel through to an even lower energy state, say in a particular domain? And if that were the case, then in that domain, the laws of physics would all be different, and it would expand outward at the speed of light, and we wouldn't actually know about it because we would cease to exist before the signals would get to our brain. They're actually, when the LHC was being planned, there was a lawsuit that tried to stop it on the grounds that we couldn't be sure that we wouldn't actually sort of induce a tunneling to a vacuum that way and destroy all of civilization. But they lost the lawsuit, and we're still here.
I thought that one of the things that quantum electro and chromodynamics did to the universe was bring in a certain amount of probability and indeterminacy.
Sure.
So these numbers on the Higgs field that you can, are these determinate, or where does the uncertainty come into the equation?
We'll actually see a little more of that in what comes up, but so if you like, this is sort of the Higgs condensate that shows here is like a bulk property, but there's going to be quantum fluctuations around the whole thing. And in fact, the fluctuations around that are what we see as the Higgs boson. And further, as we're going to see in just a moment, the proton, which we naively think of as for example, two up quarks and a down quark, when you probe closer, literally closer and at higher energies, the fluctuations involving gluons become more and more important. And so those kinds of fluctuations are omnipresent. When I say it's the most accurate theory devised by man, I mean there are observables in the theory that can be calculated. And for example, the anomalous magnetic moment of the electron, and measured, and got, what is it, something on the order of 14 decimal points that you can calculate, and 14 decimal points you can measure, and they match. And so far, nothing that we can both calculate and measure is sort of statistically inconsistent. This is depressing if you're looking for new physics.
Thank you for joining us. You've been watching Dr. Cyrus Taylor discussing the standard model of particle physics, the extraordinarily successful theory of the basic interactions of the fundamental particles of nature. For more information on the Origin Science Scholars Program, please visit the Institute's website at origins.case.edu. In the next part of the talk, Dr. Taylor will discuss how to look for a Higgs boson, the last fundamental particle discovered just in 2012 at the Large Hadron Collider outside Geneva. Now, back to the talk.
How to design a detector for the Higgs boson. So I'm going to really oversimplify the first part of this in terms of the kinds of things you're looking for. When the LHC was first being planned in the late 1980s, and the first, basically the conceptual designs for the detectors that were finally built were being worked on in the late 1980s. We really had very little idea about what the mass of the Higgs was going to be. In 1989, the big breakthrough was when Fermilab ruled out a mass of less than about 10 times the mass of the proton. And we now know it's about 12.5 times that mass. And so depending on what the energy of it turned out to be, assuming it was there, you had to be able to look at different things. The backgrounds would be different, the kinds of ways of producing it would be different. And so the detectors were designed beyond the kind of thing I'm going to talk about today, but also to ensure that it could be discovered no matter what the mass of it turned out to be. And indeed, paradoxically, where the mass actually turned out to be is the place that was about the most experimentally difficult, as seen from the point of view of the late 1980s. In any case, with the mass where we now know it is, the kind of channels that turn out to be important, if you're trying to make it something like the LHC, is where you have two gluons coming together, actually interacting with a virtual top quark loop. So this is entirely the kind of quantum fluctuations that you were talking about. You can think of this as a gluon creating a top-anti-top pair, the top spitting off a Higgs boson and turning into an antitop that, or top that continuing that way annihilates with the top and then with the gluon. And then the Higgs falls apart by a similar mechanism, in this case to create two photons. And the photons would be what you would observe. Now, again, in 1989, we had top quark hadn't been discovered, and we didn't know it was as massive as it was. This process is as important as it is because of the mass of the top quark. So the design problems when they began these detectors was much more complicated than I'm kind of glossing over today. There's another process that contributes to the same process that works roughly like this, in which you have a W boson loop. This is the very massive sort of weakly interacting analog of the photon, and again turning into two photons. And then other channels are ones where you create a pair of Z bosons, for example, and each of the Z bosons turns into, say, a muon, anti-muon pair. That's actually sort of a gold channel. Now, the problem is of course, we don't have free gluons. Glenn told you about the strong interactions last week, and so the question was, how would you make a gluon-gluon collider? And here the question of quantum fluctuations also turn out to be really important. If you think of a proton, for example, as three quarks bound together by the strong interactions, as you look at higher and higher energies, probe on shorter and shorter distances, you see more and more in the way of gluons. And again, the process of measuring what those distributions were, working out how to handle them theoretically, has been a task of decades over a series of machines. But the upshot of the whole thing is, at the kind of energies we have at the LHC, with the kind of particles that we're interested in looking at that would be relevant in Higgs production, basically the proton is almost entirely gluons. And so for the practical purposes, the LHC really is a gluon-gluon collider for the kind of processes that we're talking about here. So with that in hand, all you have to do is figure out how to accelerate large numbers of protons to very high energies and smash them together with great frequency. And so that brings us, that shows up reasonably well, to the CERN accelerator complex. And one of the virtues that CERN has had as an international organization that's been at the same location since the 1950s is, they build an accelerator, then when it's time to go to the next energy, they can use the last one as the injector into the new one. And so the process of getting protons into the LHC basically builds on decades and decades of prior investment. One of the problems that we had in this country when we were considering the superconducting supercollider in the late 80s and early 1990s was we decided not to build it at Fermilab, where you could have done the same kind of thing, but instead decided to build it in Texas, where you had to build everything from scratch. And sort of baked in from the very beginning the need to recreate an enormous amount of infrastructure with all the implications that had for cost overruns. Now, CERN exists outside Geneva. It straddles the border between Switzerland and France. And the actual ring and the detectors are sort of deep underground. And how deep underground depends on exactly where they are. On one side, you're actually getting close into the sort of the foothills of the Jura Mountains. And then, you've probably seen this photo before. You have sort of Lake Geneva in the background there to sort of set the scale. It's 27 kilometers or 17 miles in circumference. The ring was originally dug in the 1980s to create an electron-positron collider, LEP, which operated for many years. And then in this case, they reused the tunnel. They didn't have to dig a new one. That, of course, became a constraint. The maximum energy that they could get to was determined by how strong a magnet you thought you could make 20 years from the time you were designing it. The tunnel itself, is maintained in a nice, clean, modern fashion and looks very cool. Now, as a practical matter, protons themselves are not particularly large, although we'll talk a little bit more about how large they are as a function of energy later on. But the probability of knocking them together and getting a Higgs out is really extremely small. So in order to deal with that, you first of all want to go to as high an energy as you can, and then you want to go to as high a luminosity as you can. You want to have sort of as tightly squeezed bunches of protons as you can, crossing each other as often as they can. And as the machine's operating at the moment, that means in the center of each of the detectors, about every 25 nanoseconds, 40 million times a second, you have beams crossing in the middle. And the intensities are so high that the average number of proton-proton collisions in each beam crossing is about 40. So, and every one of those will generate a couple of dozen charged particles and comparable number of sort of gamma rays and so on, of comparatively low transverse energy, momentum perpendicular to the beam pipe. So it's a lot of junk. It's not very interesting, but if you're not careful, it'll fry your detectors from radiation damage. So, we'll get into the detectors a little later, but just to give you an idea of sort of the technological challenges near the beam, this is an event. This is actually a high luminosity run, so this is a bit higher in terms of the number of collisions than you see on the average in the standard running at the moment. There's 78 different proton-proton collisions here, and what you see are the charge tracks reconstructed from sort of the central tracking detector. This thing's just a mess, and there is nothing interesting in this event. And almost all the events are going to be like that. Right? This is like searching for a needle in a haystack. A couple of other views. This one, the yellow sort of shows how the charge tracks are going, and the blue shows energy that corresponds to either electromagnetic or hadronic energy. Again, it's just a mess, but it's not very interesting. And more of them. And this is a view looking at the charge tracks and the energy deposited looking down the beam pipe. Essentially what you see is a mess. So the question is how do you design a detector that 40 million times a second is going to create that kind of stuff that you're really not interested in, and yet will be able to see the rare events that you are. And I'm going to concentrate in the next section of the talk on one of the large detectors at the Large Hadron Collider, the CMS detector, which stands for Compact Muon Solenoid. And we'll see what compact means in a moment. Here's a view as they were getting ready to close it up. One half of the detector is on one side, and the other half is on the other side, and you see the person there to set the scale. And actually, it's worth seeing the first sighting of Higgs at CMS. This is Peter Higgs visiting the detector before the discovery of the boson named after him. I assume Glenn mentioned some of the history last time, but it's incredible that theorists, by sort of sense of beauty and consistency of mathematics, were able to put together something, and then within their lifetimes see sort of mankind enter on a program of testing, leading to actually the discovery of what was predicted, almost 60 years ago now. So this is sort of a cutaway of this detector when it's closed up. And we're going to walk through, actually a little later, a slice of it through here. But I wanted to give you a sense of sort of the full scale of it. I wish that were bigger. In any case, so the proton beams come in here and in here. They're circulating through here and collide in the very center here. Around that is going to be high precision solid state tracking that has about 75 million channels of electronics. That each channel of which has to be ready to say whether or not a charged particle went through every 25 nanoseconds, every 25 billionths of a second. Surrounding that is going to be what's called an electromagnetic calorimeter that's going to measure the energy coming from particles that interact electromagnetically. Then around that, another device that does the same thing for strongly interacting particles. Then we get to the actual solenoid itself. And then beyond that, the only things that's going to get out at that point are muons. And so then you've got a lot of iron here to try and keep the magnetic fields from strain, to return them, because that would be bad for all sorts of reasons. But in between the iron, you have more particle tracking detectors so that you can track down those. So this is just, we're going to spend the next couple of minutes going through this particular cross-section in a fair amount of detail. And again, as I said, inner silicon tracking, electromagnetic calorimeter, hadron calorimeter, superconducting solenoid, the return yolks in red with trackers in between. And the scale of this is, it's about 7 meters in radius. So the whole thing's about 15 meters high. So, almost 50 feet high, 5 stories, and even longer. Now, as I walk you through, while there's literally thousands and thousands of particles that have been identified as composites of quarks and so on, there's really only a handful or so that matter for what we're talking about here. These are particles that, even though some of them are decay, they live long enough that at the kind of energies they'll have coming out, they will go through the detector. So what's important are electrons. They're charged, they interact electromagnetically, they're comparatively low mass. There's the muons, which are like cousins of the electrons, except they're much higher mass, which means that as they're going through matter, they're not nearly as much as they pass by an atom, for example. So they don't radiate as much. So they don't lose energy as fast. So they punch through in a way that the other particles don't. Photons or gamma rays are neutral, interact electromagnetically. When they encounter matter, they tend to create electron-positron pairs, so you're back up to behavior like except that they're not charged. Protons are charged. They're reasonably heavy, so you don't see much in the way of electromagnetic radiation from them. And they're strongly interacting. They'll interact with the nuclei. And so when a proton encounters a nucleus, you get a bunch of junk out, and you end up with a shower akin to what happens when electrons do. Neutrons are like protons, except they have no charge. And then pions, which are quark-antiquark pairs, also live long enough that they'll make it through the detector. So they're strongly interacting electromagnetic, and for most purposes can't really be distinguished here from the protons. So as we're trying to make sense of an event, we need to be able to identify what the charge of the particles are, if possible, what their energy and momentum, or energy and direction, are, and at least try and distinguish between which of the particles before was responsible for it. So what have we got as tools for that? Well, charged particles bend in magnetic fields. So one of the key things to detectors like this is to have a large magnetic field. And so a solenoid, like the solenoid in your car, is basically a coil. You put current through it. You get a magnetic field that sort of bar magnet kind of shape. Except that the CMS solenoid is the largest magnet ever built by mankind. You see the person there for a scale. It has an internal field of about 4 Tesla, which is significantly higher than I think standard medical MRI fields over much smaller areas. There is enough energy stored in the coil to melt, I think, something like 100 tons of gold. It's big. But it has to, in order to be able to bend the particles that are coming off, enough to be able to measure the bending with the kind of detectors that you're able to put in. So that's why the central silicon tracking is so important. So this is very high resolution solid state detectors that are able to keep track, make multiple measurements of a particle as it's bending around in the magnetic field within the interior. As I mentioned, there are 75 million channels of electronics associated with it, and it is a thing of beauty, sort of exquisite beauty. And you see the various layers here, designed carefully in such a way that there's no cracks, right? Because, or at least to minimize the chance the particle would go through without being detected by some of them. And then, just as an aside, point out that with 75 million channels of electronics, there's cables that have to go somewhere. And so figuring out how to route all this, how to put everything together, how to be able to make sure when you assemble it, you know where everything is, that it will operate for years at a time because you can't go in to fix things easily. The engineering challenges are extraordinary. And of course, none of the technology to do any of this existed at the time that the detector was initially designed. So part of the challenge in building these is you start at time t for a detector you're going to operate 20 years hence. Try and figure out what the technologies will be at that time. Develop them along the way, and then have several competing paths so that if something doesn't work, something else will. So continuing is the electromagnetic calorimeter. CMS uses a lead tungstenate. It's a very clear glass with a lot of lead in it so that gamma rays coming in, for example, shower. As they shower, they end up creating light. The light gets collected by basically photodetectors, and the energy of the particle coming in is proportional to the light that you measure. So it is, again, a thing of beauty. Hadron calorimeter. The central portion is kind of interesting. It uses scintillating plastic in between layers of brass. The brass is largely made from recycled Soviet artillery shells from the Soviet Navy in World War II. So it's one benefit of the Cold War in terms of keeping costs down here. There's actually a couple of different calorimeters depending on the position in the detector. The picture here actually goes in the forward region. This is steel with quartz fibers in it. What happens is as the particles go through, they create Cherenkov light within the quartz fiber, and you pick those up. And so this is more resistant to radiation than what you need in the central region. Then finally, as I said before, the only thing that will get basically through the hadron calorimeter and the superconducting coil are muons. So in between the return yolks of the magnet, you basically have tracking chambers there, and that's what you see here. Questions?
What's the temperature of the superconducting solenoids? Then? Is it?
Oh gosh, I wish I remembered that offhand.
I mean, is it cryogenic?
Yeah, absolutely, it's cryogenic.
But like
yeah.
minus 460 up or 273?
Okay,
that's what I want.
Yeah, these whole things are formidable cryogenics, and the other detector actually uses liquid argon as part of the detection process. So, everything about this is technologically challenging.
Is this in a vacuum, and if so, how on earth do you make?
So the only part that's in the vacuum is actually within the beam pipe. The rest of this...
Well, that's still a lot, isn't it?
well, the beam pipe itself, yeah, it's still a lot, and it's 27 miles or 27 kilometers long of a vacuum that's a higher vacuum than anything short of interstellar space.
Yeah, that's what I was wondering, how low you get it.
You pump very hard.
We hope you've been enjoying the Origin Science Scholars Program with Dr. Cyrus Taylor. Dr. Taylor is the Albert A. Michelson Professor in Physics and Dean of the College of Arts and Sciences at Case Western Reserve University. In the second part of our talk, we learned about CERN, its Large Hadron Collider, and the Compact Muon Solenoid, or CMS detector, that was used there to co-discover the Higgs boson. In our final segment, Dr. Taylor will talk about the prospects for future exciting physics at the LHC. Now, back to our talk.
What I wanted to do is put this all together now. And let me make sure that this is going to work. So there you see a muon going through. And you see what I said before. With a muon, you see the tracks within the charge detector, and then you see a track out here in the muon trackers outside, and you see nothing in between. That's sort of the signature of a muon. Then we've got electrons. You see the electron going through the tracker, so you have the tracks, and then you have energy deposited in the electromagnetic calorimeter. And we have a charged hadron. And so we end up with the tracks in the central tracker, essentially little energy in the electromagnetic calorimeter, and then a shower in the hadron calorimeter. You see nothing essentially until, if it's a neutral hadron like a neutron, until it gets out here into the hadron calorimeter, and then you see energy. And then finally a photon. You don't see anything until you see energy deposited in the electromagnetic calorimeter, and you don't see anything after that. So depending on what the signal is that you see in each of the different detector systems, you can figure out what the energy of the particle was, which direction it was going, and what type it is. So how does this work out in practice? So let me show you a couple of events. So this is a candidate Higgs goes to a 4-electron event. These events are actually from runs that were fairly low luminosity, so you don't see the background junk. These were from early in the LHC commissioning. And so you see some background junk from, these are the various yellow particles here that are more or less completely uninteresting. But the important part here is you see 4 electrons. You see the tracks in green. And then each one of them has energy deposited in the electromagnetic calorimeter and nothing else. And the energy of these adds up to the energy of the Higgs boson. Here's another one. This is looking down the beam pipe. And so you see the same thing. You see a bunch of pions that are uninteresting. You see 4 electron tracks in the tracker, denoted in green here, each one of them pointing to energy being deposited in the electromagnetic calorimeter. And again, the sum of those adds up to the mass of the Higgs boson. This is a process that we looked at earlier with the Feynman diagrams. Higgs goes to gamma gamma. Again, you see a bunch of pions that are uninteresting. Some energy being deposited in the forward direction in the electromagnetic calorimeter and the hadron calorimeter. But what's really significant about this event is basically 2 cells of the electromagnetic calorimeter light up. Again, the energy adds up to the mass of the Higgs boson. You don't see anything actually in the inner tracker. And then this is sort of the gold-plated kind of signal. Higgs goes to muon, anti-muon, muon, anti-muon. And again, this is looking down the beam pipe. You see, and the scale is much larger here because the muons basically go through the entire detector, whereas before we've looked at sort of the central part. So in the center, you see the typical pion junk from just the random debris of the rest of the protons. There are 4 tracks coming out that basically get picked up in the muon detectors, don't deposit any energy in the electromagnetic calorimeter, don't deposit energy in any energy in the hadron calorimeter. So you know they're muons, and they add up. Now, the reason I call them candidate events is because there are backgrounds. There's all sorts of other things going on that can mimic these, particularly when you have multiple collisions like that. And so this is how the CMS detector, the collaboration, modeled the background. They have to understand the detectors very well. They have to understand all the physics, not just the physics that's really interesting very well, to be able to model what the detector response would be if there wasn't anything there. And that's sort of the blue curve here. The data are the dots, and what you see is there's a peak that involves a significant excess above the background at about 125 GeV. And then looking at the other detector with the gamma-gamma signal, the background is sort of a slowly falling, or rapidly falling, depending on how your perspective, and then you have a bump here. So you have to understand the backgrounds really well, and if you think you do, you can subtract the background from what you see, and you see a bump, which happens to be at the same energy. And so, part of the game of the detector is to look at every single process that you can think of that's sensitive to it, model the backgrounds so that you understand them really, really well, and see if what's left is consistent with the properties of a Higgs boson. And this basically, the last time I came and talked to this group was 5 years ago. The Higgs hadn't been discovered yet. It was formally announced, I guess, about 6 months later. That was very exciting. It's led to big prizes as a result. It's been something of a disappointment, of course, that we haven't found anything beyond the standard model, right? There were all sorts of theorists that come up with theories for other particles that if their models were right, should have been seen, and we don't see signs of any of them. It's been the same story with accelerator after accelerator. And instead, what we're in the business of, it seems, is doing sort of precision tests of the standard model to see if all the properties of the Higgs boson and everything else really matches that set of equations that fit on a coffee cup. So the future for this, there's certainly still some possibility of major discoveries, although it's getting smaller. Not everyone has paid off their wagers yet. And the machine is moving to steadily higher luminosities, bigger data sets, more channels of analysis, and kicking the tires of the predictions in steadily greater fashion. So this might actually be a time to pause. If you don't know, okay, I'll keep going. I pay attention to what Patricia says. So let me talk a little bit about an experiment that I've been involved in, really for about 20 years now. It's called Totem, which is also at the LHC and sort of sits in the nooks and crannies around CMS, which was part of the reason why I picked CMS. So this is a cross-section along the beam of the CMS detector. And what you see is sort of the central barrel here and then the end caps of it. It's a long story for beyond the scope of this talk as to why I got really interested in building a detector that would catch all the particles that were produced in collisions at the LHC. But the short version is, and the reason we were able to sell the experiment in the end, is someone actually has to measure what the size of the proton is at that energy. And it could not be done just with the central detectors there. They're particles that basically go down the beam pipe that the major detectors were unable to see. So what Totem consists of is on each side of the CMS detector, there's sort of three kinds of detectors. There's a charged particle tracking that sits just under sort of the return yolks in the front direction. There's another one that sits just beyond their forward hadron calorimeter. And then at distances of about 150 and 220 meters away from the collision point, so like 1.5 and 2 football fields on either side away, we put silicon detectors actually inside the beam pipe, approaching to within about 1 millimeter of the beams, so that protons that have just been sort of gently bumped end up getting detected. There's three different technologies that are used for it. The first one, the T1 tracking telescope, all of these have to be really radiation hard because the backgrounds in these regions are just a nightmare. The T1 one used a fairly conventional and known technology. T2 was actually a technology that was developed working with our collaboration and has turned out to be really successful. It's an inexpensive, accurate, radiation-resistant way of tracking charged particles with high precision. And then the final part of what are called Roman pots, because it was a group from Rome that first devised a scheme in which you could put detectors to within about 1 millimeter of the beam. They're not actually in the vacuum. What we have is sort of silicon detectors that fit within a very thin kind of metal housing for it that then gets lowered within the vacuum to, as I said, about 1 millimeter from the beam. This makes people very nervous, as you can imagine. At Fermilab, an experiment that was trying to do this, there was a glitch, and it resulted in unfortunate things happening. Here you can see some of the mechanics. We have some that go in both vertically and some that go in horizontally, depending in part on the niche. And there's 2 stations. Each station, there's multiple measurements so that we can get a good pointing in both directions. This is an old photo of my longtime collaborator contemplating some of our Roman pots. And so, the physics we used to sell it on was, as I said, not the most exciting. It was measuring the size of the proton. But it actually has to be measured so that you can normalize everything else to it. And the problem was at Fermilab, there were 2 measurements, and they disagreed each other by quite a bit. And we were able to resolve it with a fair degree of precision. The various other measurements here were inferred from cosmic rays and basically provided little information. So in any case, after 20 years of working on this, we're finally in a position that we're integrating what we're doing with CMS itself. And so there's a joint collaboration, CTPPS, which is CMS Totem Precision Particle Spectrometer. We look for protons on each side that have been scattered, and then look in the central detector to see what stuff is there. We're in the process of adding in, or have added in, additional Roman pots for greater tracking. And now we're able to do things, these events are quite clean. So you have stuff going on in the center, you don't have the accompanying junk, and there's all sorts of interesting physics that can be done there.
What do you mean by bad things happening at Fermilab?
Yeah, you know, it's just generally not a good idea to put metal and silicon in the path of a beam that has as much energy as the beam had. It requires repairs.
Could you describe the process of all these different people involved in these devices agreeing on how the design and building?
Oh yeah. So there's a couple of really interesting aspects to that. So first of all, the organizational structure of collaborations like this is really important. In terms of sort of a self-governing bureaucracy, in terms of following all of this, it's, I think, one of the wonders of mankind. Because remember, most of these are incredibly multinational collaborations, often involving scientists from countries that are not actually friendly with each other. The second thing is just the sheer logistics of it was such that CERN in, I guess, around 1990, started a special project to try and figure out how high-energy physicists in this project could share designs, data, and so on and so forth. And they called it the World Wide Web. And in April 1993, granted the world a royalty-free license to use it. But it's in terms of thinking about those kinds of things that was actually responsible for something that's changed the lives of all of us. It can be formidable, and I don't want to underplay the role of politics, right? Each of the members of the collaborations has to work with their own funding authorities in order to get funding for their own projects. Coordinating all of this is as I said, I think it's a testament to the spirit and skills of humans to work together for common purposes over long periods of time under insanely tight timescales and pushing technologies to the limit. It gives me hope for everything else. So thank you.
The Origin Science Scholars Lectures are presented by Case Western Reserve University's Institute for the Science of Origins, with the assistance of the Siegel Lifelong Learning Program, the College of Arts and Sciences, and MediaVision. For more information on the Origin Science Scholars Program, including a full video archive, please visit the Institute's website at origins.case.edu.